So welcome back, and I would like to start today's session with an example on splitting fields. So suppose you would like to get a polynomial, a splitting field of the polynomial x to the 4 minus 2 over q. Okay, so the potential roots of this polynomial, when you factor it over the complex numbers, over the complex numbers, this we didn't discuss, but over the complex numbers, every polynomial splits completely to linear factors, and this polynomial is no different. Specifically, you could write x minus, or let me say the roots of f are one pair of roots is a fourth root of 2, but it could be a positive or negative. And another pair of roots is a fourth root of 2 times I. Okay, and since we know that a polynomial cannot have actually this would be here, it would be it should still be a fourth root of 2. And this is the complete set of roots, but none of these roots belongs to Q. So over Q, f is prime. In Qx. Okay, so what do? We have a recipe to construct the splitting field of f. We look first at q of x modulo f, and this we know by general kind of abstract reasoning that this is a field with a root, let's call it alpha of f but f considered as a polynomial in K1 of x. Now, again, this alpha is kind of an abstract root that was derived from a meta trick, but and we could choose either of these these roots to be alpha. I mean, from the point of view of the this first extension K1, it doesn't matter because alpha is kind of I mean, K1 would be Q adjoint with alpha, namely the minimal field containing Q and containing alpha. And alpha is just some kind of creature that if you raise it to the 4, you get 2, right? So say alpha is equal to square root, sorry, fourth root of 2. Then I look at Q of fourth root of 2. This is like you doing the complex numbers, right? I mean, you look at all the expressions of the form a plus b fourth root of 2, where a and b are elements in Q. And this is at least isomorphic to K1. So over K1, I can say that fx is x minus square fourth root of 2, x plus fourth root of 2. But there is another part which is not yet decomposed or splits, and this is x squared plus square root of 2. Okay, over K1. So what do? I take the part of f that is not linear, and it is assuming it is a prime. I mean, of course, we can see that this is prime because the roots of this needs to be something with I, and I does not belong to this first extension K1. So what I need to do is to further divide. I define F1 to be x squared plus square root of 2. And now I look at K1 x modulo x squared plus square root of 2. Okay, and here I am guaranteed to have F1 has root, say, alpha 1 over this new field, K2. And it means that K2 is the minimal extension of K1 containing alpha 1. Now, again, there is a flexibility. I mean, alpha 1 could be either plus or minus fourth root of 2 times I. But it doesn't matter because the minimal field containing K1 and fourth root of 2 times I is the same as the minimal field containing k1 and fourth root of 2 times I times -1, right? So you see, once you have either of them, you get automatically the other, and so F1 splits over K2. Namely, I could write F1 equals x minus fourth root of 2I x plus fourth root of 2I. And since F1 splits, then I get automatically that the original polynomial F splits and we get that K2 is the splitting field. At least a splitting field. Of F over Q. Okay, and K2, you could write it as basically all you need is to adjoin the fourth root of 2 and the element I. Once you adjoin these two, you have everything you need. I mean, and that's the minimal thing you can do. Minimality also follows from minimality in each of the stages. I mean, here, or maybe here, since K1 is this Q adjoined fourth root of 2, K1 is the minimal field containing Q and fourth root of 2. And similarly, K2 is the minimal field containing K1 and fourth root of 2 times I. So all in all, K2 is the minimal field in which F splits. Okay, is this clear?
I have a question. When we introduced Qx as over F as K1, by Qx, did we mean polynomials whose coefficients belong to rational numbers, or we just called it Qx?
Yeah. That's the notation. I mean, if I write Fx, it means polynomials whose coefficients are in F, in a field F.
Yeah,
okay?
But at some moment we also had I, but we didn't introduce Cx.
Yes, but well, this is all kind of under the umbrella of the fact that C is contained in, sorry, a Q is contained in C.
Okay.
Right. So, I mean, this example is simplified intentionally. So I know in advance what are the roots I'm looking for, and that's why it's easier to explain. But the general construction does not care about what you do. I mean, what you know in advance. You simply mod out by a prime polynomial. You're guaranteed to have at least one root after you mod out by this prime polynomial. And if it splits completely, you stop. If it doesn't, you keep doing it. So it doesn't matter eventually. I mean, you don't need to know the roots in advance to know that this construction eventually terminates into a splitting field of the polynomial. Okay, so
Yeah.
this is just to be a bit more concrete. I wrote the roots in advance. Okay, so this is how you go about splitting fields, and what we proved last time is that splitting fields are unique up to isomorphism. Splitting field for if is unique up to isomorphism, i.e., if E prime is also a splitting field. F then we get an isomorphism between E and E prime. Yes, there was a question?
Yes, I think this is what you hinted before, but for K2, you define it very generically with just a potential root alpha. And then you directly said that alpha is I or something like I just missed the step, but while you define it generically from K2 to the this step here. So you define K2 for K1 adjoint with alpha 1, but
No. That's the definition.
Yes.
K2 is you take K1, you take whatever is left after you split off linear factors from F in K1. You take whatever is left, we call it F1, and you mod out by it.
Sure.
Okay, that's the definition. And what we showed last time is that this kind of construction is always isomorphic to simply adjoin. I mean, take K1 and adjoin some kind of abstract root to the polynomial you mod out with.
Okay, so because you're saying this, then alpha 1 can only be I. Can only be alpha 2 I, square root of 2 times I.
I mean, alpha 2, sorry, alpha 1, it needs to be a new root.
Yeah.
Right? I mean, of course, fourth root of 2 is also a root of this polynomial.
Sure, it's already contained in K1. So
but it's already in K1.
Yeah.
In order to, since I know that K2 has a new root, then I know that alpha 1 is either fourth root of 2 times I or minus of it.
Makes sense.
I mean, this
Thank you.
Okay. So, and the splitting field is unique up to isomorphism. Now, using this fact, we are going to classify all finite fields very easily. But I need one more ingredient. Let me call it an observation. So let F be a field. And let's say I have a polynomial of the form sum ai x to the I equals 0 to n. A root alpha of f is called repeated root if not only that you can write fx equals x minus alpha times gx, but you can write it at least with a power of 2. I mean, potentially more, but at least with degree 2. Okay, for some g of x. And what I claim is that there is a simple criteria to see when a polynomial has a repeated root. Consider the formal derivative df, which is simply the polynomial sum I times ai times x minus 1 I equals 0 up to n. Okay, this is like it's like doing the derivative that you know from school to this formal expression. I mean, you know how to do derivative to each of the monomials, and you sum it all up. And I claim that f has a repeated root, or let's say if f has a repeated root, then f and df have a common factor of a degree bigger or equal to 1. Right? That should be obvious, because if f has a repeated root, then I can write fx equals x minus alpha square times gx. And this would mean that df of x is 2x, 2 times x minus alpha times some g prime of x, right? So all in all, I get that x minus alpha is a common factor of f and df. Okay, is this point clear?
Yep.
Okay, so now we get to the main goal, and this is the I guess you can call it structure theorem of finite fields. And the claim is you fix a prime then for any n in n, there is a field FQ with Q equals P to the n elements. Moreover, FQ is unique up to an isomorphism. Okay, so this is the result we were aiming for, and the proof now should be very easy to follow, since we talked about all the ingredients. So the statement, of course, it has two parts: existence and uniqueness. So let's first do existence. I consider the polynomial x to the q minus x in fpx and I let E be a splitting field of F. And now, clearly, the characteristic of E it must be P, because E has to contain FP, and once a field contains FP, it has to have a characteristic P. This we discussed, and I claim so. We may view F as a polynomial over E. Now, since the derivative of F is Q times x to the Q minus 1, but Q is a power, yeah, I didn't say it, but okay, yes, I guess I did say it here. So Q is a power of P, and therefore Q is equal to 0 in any field of characteristic P. So this is -1. And since I know the derivative of f is simply a constant, then it cannot have a common factor with f. So I know that f has no repeated roots. Okay, now I consider now the set of all roots of f. Let's call it k. This is all the a's in E, such that a to the q minus a is equal to 0. And I claim that k is a subfield of E. Now, how do you see it? So, first of all, 0 is clearly contained in k. I mean, 0 is indeed a root of the polynomial x to the q minus x. Now, suppose I take two roots and I add them together. I want to know that if I add two roots together, I still get a root. I mean, I want to know that k is closed under addition. But I also want to know that k is closed under additive inverse. So there is a quick way to do both of these axioms in one go by doing the following. If A, B are elements in K, then I can use this, remember this freshman exponentiation? I mean, if you do A minus B to the Q, it's the same as A to the Q minus B to the Q. I mean, we had it for P. In any characteristic P field, A minus B to the P is A to the P minus B to the P. Remember this? And by a trivial induction, you get the same result for any power of P. I mean, I mean, take U equals P squared, for example, then you simply apply this principle twice and you get the result. Is this clear? So, of course, if I have this equality, then since A and B are roots of the polynomial f, then this is simply A minus B. So A minus B is indeed an element in K. I mean, A minus B to the Q is A minus B. It means that A minus B is a root of the polynomial f. So here, in one go, I checked two of the axioms of a field, namely, or of a subfield, namely that it is closed under addition and under additive inverse. And similarly, I can check in one go that it is closed under multiplication and under a multiplicative inverse. And that I do with the following. I mean, I take some A and B in K. Let's say B is non-zero. and I do A times B minus 1, I want to show that it's again an element in K. So I raise it to the power of Q. But if I raise it to the power of Q, it's the same as doing A to the Q times B to the Q minus 1. And since A and B are in K, namely roots of the polynomial f, this is simply A times B minus 1. So I get that A times B minus 1 is again an element in K. Okay, so K is a field, and it's a field contained in E. Yes.
Sorry, maybe it's very simple, but why again can you simplify A to the K equal A?
A to the Q equal A?
A to the Q, sorry, A to the Q equal A.
Because A is in K. The K is defined to be the set of all roots of the polynomial f over E. Right? I take E as the splitting field of F. And I know that F does not have repeated roots, in fact.
Mm-hmm.
And so now I look at the set of all roots. We know that the set has to be of size Q, right?
Mm-hmm.
And now if A is an element in K, then by definition, A to the Q is equal to A. Because A to the Q minus A is equal to 0.
Oh, sorry, yes. Okay. It's stupid. Okay, thank you.
No, that's completely fine. I mean, asking silly questions is the fastest way to learn.
Perfect. Yeah, makes sense. I had a second one, so I can just jump in. Why? Because you said you mentioned it before, but I'm not sure I quickly see why there is characteristics P in E. Why E has characteristics P? Because
because E is an extension.
Yeah.
E is an extension of FP.
Yeah.
Once it's an extension of FP, it has to have characteristic P. Because I take 1 plus 1 plus 1 P times. Since it's 0 in FP, it has to be 0 in E. I mean.
Yeah. Okay, makes sense. Yeah.
Okay.
Sure. Thank you.
Okay, so I know that K is a subfield of E. But F splits over E. Over K, because K contains all the roots of F. And since E is the splitting field, if you recall, it's the minimal in which F splits. It means that K has to be equal to E. And thus I get that I have a field of Q or P to the n elements. Okay, so this is existence. So I take E, a field with Q equals P to the n elements. then of course E must be of characteristic P, right? So I have an isomorphic copy of FP inside E. Okay. And now I take a look at what I call E star. This is simply you take E, you remove the zero element, and you consider it as an abelian group with respect to multiplication and the unit element 1. So this is an abelian group. Of size Q minus 1. So for every A in E, A to the Q minus 1 must be equal to 1, which is completely equivalent to say that A to the Q minus A is equal to 0. This is for every element in E. Thus, E is contained in a splitting field of this polynomial f, x to the q minus x, over the ground field f. Since we know that E has q to the, or I mean, p to the n elements already, then it must be a splitting field itself. This was what we showed in the existence. And uniqueness now follows from uniqueness of splitting fields. Okay, this is the end of the classification of finite fields. Any question about the proof? Is it clear? Okay.
Maybe a phone question. So, you defined f of x as x to the q minus x, but this could be any set of polynomials because you can sum any constant here of degree 0, and this is a complete, maybe not a completely different polynomial that characterizes f. So, is there any issues on that the fact that the polynomial is not unique, or it just simply doesn't matter?
I mean, of course, you're saying that I could write, I could take fx to be some lambda times x to the q minus x.
For instance, yeah.
Yeah. Why is it not an issue? First, the potential. I mean, the roots of f. Let's call it f prime. Okay.
Oh, I see. Yeah. Okay.
The roots of f prime are the same as the roots of f.
Yeah.
Now, all I'm saying is that I mean, there is a splitting field for f prime or for f, whatever you choose.
Yeah.
And this splitting field has to be unique up to isomorphism. And what this proof shows is that, in fact, every field of q to the n, or I mean p to the n elements, it has to be this splitting field, because I mean, in any field of q to the n elements, I have a to the q minus a equals 0 for every a.
Yeah.
Okay.
Yeah.
So it means that the polynomial splits completely. So it's a splitting field, and hence I have no. I mean, up to isomorphism, I have no choice.
Sure. Thank you.
Okay. Let's do something short before the break. So we know that we can construct a finite field using this splitting method, but we also know that we can construct a finite field by modding out polynomials by some prime polynomial. And the question is, I mean, if phi is a prime polynomial of degree n, then fx modulo phi is a field and the number of elements in this field is simply the number of elements in f to the power of n. Right? Because k, I remind you of our definition, it's the set of all remainder polynomials by taking a long division with phi. So this is all a set of all, let's say, Rx equals A0 plus A1x plus AK x to the k, where the AI are in F, and K is some integer strictly smaller than n. And you have exactly F to the n possibilities for Rx. So potentially, I could say if I take F to be Fp, then Fpx modulo phi is a field of p to the n elements, right? And we know by the general, the structure theorem, we know that this field will be isomorphic to the splitting field. I mean, there is only one field up to isomorphism of size p to the n. This field is often denoted as FQ. You can also denote it as a Galois field of P to the n. Now, the question is, can I find a polynomial which is prime over Fp of any given degree? If I can do that, then I have a very, well, I have an alternative construction, right? But we don't know how to find a prime polynomials of every given degree. I mean, there are algorithms and so on, but we haven't discussed it. It's quite involved to look at it. But what we could do is to come up with this proposition. Let P be prime. Then for any integer n, there exists some n bigger than n with or and a prime polynomial phi of degree n. Okay, so the proposition tells you we might not know, at least at the moment, how to construct a prime polynomial of every given degree, but I can go as large as, I mean, I can go infinitely in infinitely high degrees. And the proof is actually very simple. Assume by contradiction that the claim is false. If the claim is false, it means that there are only finitely many prime polynomials over Fp. And let's enumerate them. I call it phi1 up to phi k. But then you take the product and you add 1 to it, and you get a new prime polynomial. Let's call it phi. Since phi I does not divide phi for every I. Okay, and that's a contradiction. And if you think of it, what I did here is simply taking the proof that there are infinitely many prime numbers, and doing the analogous proof for prime polynomials. Okay, so at least this proposition guarantees that you can find prime polynomials over Fp of arbitrary degree. Let me just mention, why if I assume that the claim is false, I know that there are only finitely many prime polynomials, because Fp is finite, and if so the set of all polynomials of a given degree d over Fp is a finite set. So if I know that the degree cannot be, the degree of prime polynomials cannot exceed some number n, then I know that there could be only finitely many polynomials up to degree n. In particular, there will be only finitely many prime polynomials. Okay, is this clear? Are there any questions? All right, so let's take a break and come back to another claim of finite fields, and then some kind of revision that I postponed until now. All right, so we have a classification of finite fields, but there is still the question, well, we know that the additive group of a finite field is isomorphic to the direct sum of copies of Fp, and so if Q is P to the n, then we know that the number of copies of Fp here is exactly Q. Sorry, exactly n. Right? We did this with the classification of finite abelian groups. But if you recall, the classification of finite abelian groups had two versions. And now I claim, I mean, using the second version of classification of finite abelian groups, we can also pin down the multiplicative group, I mean, the multiplicative structure of the field FQ. So this is the next theorem. Let P be prime. And take Q some fixed power of P. Then the multiplicative group which we denote as FQ star, right? This is you take FQ, you remove the zero element, and you look at this set with the multiplication given in the field FQ and the unit element 1. And I claim that this group is cyclic. That is, there exists some element eta such that the order of eta is precisely the order of the group, which is of course Q minus 1. Okay, this eta is called a primitive. Okay, so how do we go about proving this claim? I let n to be the maximum of all orders of elements x in the field FQ. Okay, or rather in the multiplicative group FQ star. Now, by Lagrange, the order of every element it needs to divide the size of the group, which is in this case Q minus 1, or P to the n minus 1. So in particular, n must be smaller or equal to P minus, well, to P minus 1, P to the n minus 1. And now applying the second version of the classification of finite abelian groups, we get that the multiplicative group of FQ it must be isomorphic to integers modulo M1, direct sum integers modulo M2, direct sum integers modulo MR, where each of these MIs divide the next one. And now, okay, what you need to remember is that here FQ is given in multiplicative form. This is the left-hand side is multiplicative, and the right-hand side is given in additive form. Okay, so but what we can conclude from the left-hand side, this guy, what is the order of, I mean, what is the maximal order of an element in the left-hand side? Sorry, in the right-hand side. The maximal order of an element in the right-hand side is simply MR, right? You cannot do better than MR. So it means that N is equal to MR, right? Isomorphic groups have precisely the same distribution of order of elements. For any x in FQ or in FQ star, the order of x must divide MR, right? Because again, look at the right-hand side. Since each of the MIs divides MR, the order of every element in this sum must divide MR. So this is true also for the left-hand side. And what it means is that x to the n minus 1 is equal to 0. Write it in different forms. The polynomial x to the n minus 1, when I think of it as a polynomial in FQ, right, this is supposed to be capital X. Admits at least a Q, which, Q minus 1, which is P to the n minus 1 roots. And if it admits a P to the n minus 1 roots, it means that that n is I mean, you see, we know that n was less or equal to p to the n minus 1, but this this part gives us that n is greater or equal to p to the n minus 1, because a polynomial of degree n can have at most n roots. So I get this this funny inequality, which means that n is equal to p to the n minus 1. But n was defined to be the maximal order of some element in FQ or FQ star. So we conclude that there exists eta in FQX such that eta to the q minus 1 equals to 1, which means that FQ star is cyclic. Okay, so this is the basically pinning down the multiplicative structure of a finite field. Any questions about this this result? I get a feeling that something is maybe not completely clear, or is it? Yes.
Okay, yeah, I'll go ahead. For the last point of the proof, something I'm not sure. Can you go down to the last?
Sorry, say again.
Sorry, can you go down to the last point of the proof? I understand most of the proof, I think, but maybe the last point is not clear. Like, how do you? Sorry, no, maybe when you say order of x equal n on top of the screen that you have now, then you say that the polynomial x to the n minus 1 admits at least q minus 1 roots. This is, for me, I'm not sure how do you see this, because n is just defined as a maximal order, but we don't, I'm not sure why you say the polynomial x to the n minus 1 admits at least q minus 1 roots.
Yeah, so I take any element in FQ. Maybe it's better to call it in different names. Okay, I call it A. Okay, I look at this side of the isomorphism. A has an analog here, right? Let's call it maybe A bar. Okay, right? A is typically is originally chosen here, but using the isomorphism, I can find a bar here with the kind of same properties. Now, every element here on the right hand side has an order that divides MR.
Yep.
Okay, so I know that the order of A also on the left hand side must divide MR, but MR is n.
Okay.
Okay, if the order of A divides n, it means that A to the n is equal to 1.
Yes.
Or A to the n minus 1 is equal to 0.
Yep.
So the polynomial x to the n minus 1 has, I mean, every element in fqx, if fq star, is a root of this polynomial, and I have a q minus 1 elements here.
Okay, yeah, makes sense.
Okay, so the polynomial x to the n minus 1 admits at least, well, at least, I mean, admit exactly, well, okay, so admits q minus 1 roots. So, or p to the n minus 1 roots. So p to the n minus 1, it has to be smaller or equal to n, because you cannot have more roots than the degree of the polynomial.
Yeah, the rest was clear. It was just this point. I think it's clearer now.
Okay.
Thanks.
Okay, it's a very simple reasoning, I think. The crux is that I use this the second version of the classification of finite abelian groups. So this kind of, it shows you why it's good to have this flexibility of the two versions. All right, so I think in the remaining time, I would like to do a revision of what happened in this this whole track of classification of finite fields. Next time, we will start with what is called the algebraic closure. And this will be important later on, but for now, let's kind of crystallize what we did. So the main issue with this classification of finite fields, and this is something that of course will be useful later on, is this analogy with between integers and polynomials over a field in one variable. Right? So here you have you can say the integer n, it may correspond to a degree n polynomial. And then there is this notion of a prime, and we have this this analog in polynomials of prime polynomial. Then we had a long division. So if I want to let's say I want to write, I want to divide k by n, then I get some quotient and some remainder, with the remainder strictly smaller than n. And the same is true for polynomials. So if I get let's say I do g is equal to f times q plus r, where r is of degree smaller than the degree of f. And using this long division, we proved that there is this there is a GCD. I mean, here you have a GCD of K and N. GCD of K and N is simply you take the prime factorization. Let's say P1 to the A1 up to PR to the AR, and you take let's just say that the prime decomposition is over the same set of primes. Sorry, then in this, if it's in the same set of primes, then this is PR to the BR. And the GCD, you just take the maximum, right? You take, but this is all based on the fact that in integers, there is a unique decomposition, unique up to shuffling the order. There is a unique decomposition of an integer into a product of primes. And we proved that in polynomials over a field, you have the same kind of factorization. I mean, you have a unique factorization of f into polynomials. Maybe I can write it here in the same way. With PI prime polynomials. And we showed that this factorization is unique, at least when f is monic polynomial. This factorization is unique up to shuffling the order of the components. I mean, of the different factors. So using the fact that I have a unique factorization into a product of primes, I can define at least for monic polynomials, I can define a GCD of f and g. Right? And I mean, of course, if f and g are not monic polynomials, the GCD is almost unique. It's not unique. It's unique up to a multiplication by a constant, by an invertible element in the field. So this is basically corollaries of the fact that I can do long division. And in fact, using this long division, I mean, we saw that you can also lift the Bezout lemma. Bezout lemma it tells you that if you have any two integers, a and b, there exists some u and v such that au plus bv is equal to the GCD of a and b. These U and V are called the Bezout coefficients, and they're generally not unique, but it's enough for us that they exist in order to do what we want. Namely, in the case of integers, we wanted to prove that integers modulo p are a field. And how do you do it? Well, you all you need to find is a multiplicative inverse. So for a in integers modulo p, of course, the GCD of a and p is 1. So there exists some u and v such that au plus pv is equal to 1. But this means that au is equal to 1 modulo p. So u, this first Bezout coefficient, is one option for the multiplicative inverse of a. But the same, almost, verbatim, the same argument can be applied to polynomials modulo a prime polynomial. Namely, you take phi to be a prime polynomial, and you look at, first we denoted this, well, anyway, you look at polynomials modulo phi, and you have addition and multiplication modulo p, so it is a ring, and all you need to show in order to show that it's a field is that there is a multiplicative inverse. But let's say phi, just for simplicity, phi is a monic polynomial, and I take another monic polynomial a, then I know, because phi is prime, I know that the GCD of a and p is 1. And the Bezout lemma that has a version in terms of polynomials guarantees that I have polynomials u and v such that au plus pv is equal to 1. And this means that p was p here is denoted as phi. So I get that au is equal to 1 modulo phi, and this means that u is a multiplicative inverse in fx modulo phi. Of course, if phi is not monic, then it is a constant times a monic polynomial. So you can simply apply the same argument for the monic polynomial that you extract from phi. And the multiplicative inverse will then simply be the constant times the multiplicative inverse with respect to the monic polynomial. So all in all, fx modulo phi is a field. Okay, so this shows you how far the analogy between integers and polynomials can take you. It's I think it's quite quite surprising that you could use this analogy for that long. We have more steps, mainly regarding the splitting fields, but let's say on this part, is there any point you want more clarification?
I think from the reactions of everyone, it was pretty clear.
Okay. So once we have this, then we showed that in fx, yes. Now?
No, was just a message. I didn't want to interrupt. Sorry. I was thanking you for linking all the links.
Yeah, sure. But as somebody else raised a hand or something, I heard a ping.
I think the ping was from the message.
Okay. So the next step was to show that in fx modulo phi, which we can call k, phi has a root. This is the heart of the matter, really. So I'm happy to repeat this kind of argument. I mean,
Can we? Sorry, Matan.
Yeah.
Will it be possible? Because I think as it happened on the last minutes on the last session, when we went also through a pretty long proof or extensive proof, is it possible to review this during the week and at the start of the next session? Ask
You mean
questions if anyone has the review of the entire thing?
you mean the uniqueness of splitting fields up to isomorphism?
Yep.
Yeah, sure. Let me try to do it now, even. Okay.
Maybe even the existence.
You're talking about existence or uniqueness of splitting fields?
Existence. So we
Okay.
we went through the entire thing and we said let's like leave this week to like study in between and review the entire thing and then go back to it, and if anyone has questions on the next session, ask them. So I was wondering if we can do the same with the Galois wheel and this mapping that you just shown to us, where we can link polynomials to fields.
I'm just I don't understand what part you want to review.
So what I want is to have time by myself to go through it again and see if by myself I understand it, such that then I can ask questions on the next session, or I can just like.
Sure. This is always yeah. This is always open. I mean, you can always review any material we did and ask a question in the next session. This you should feel free to do always.
Okay, because I say because it feels that maybe it can disrupt the order a little bit, because we maybe have transition to a different topic or something like that, and it kind of brings back the discussion or whatever. So.
Okay, so yeah, I see now a question in the comments about existence of splitting fields. So let me try to review this part. So I take a K to be the field of fx modulo phi, right? We know that it is a field. And now I look at polynomials over K. So, or maybe before we do this, of course, our definition of K was all the remainder polynomials with coefficients in F and with degree strictly smaller than n, where of course the n is the degree of phi. Okay, and the addition and multiplication of elements in K is you simply do addition or multiplication of polynomials, and then you reduce modulo phi. So in particular, F is contained in K because you can take the remainder polynomial which is just a constant, just A0. And this will amount to every element in F can be presented as a remainder polynomial of degree 0. And now I can look at a Kx, but for disambiguation, we denoted it as K with capital X. And the reason is that K with capital X is like a polynomials R0 X plus R1 X, and then plus let's say RD X to the D, where these guys R0 up to RD are polynomials, I mean, are elements in K. But elements in K are remainder polynomials. So this is kind of a meta trick. Now I look at polynomials with coefficients being polynomials. But remember that if I add two elements in K, if I do, for example, R0X plus R1 X, capital X, and I want to multiply it, let's say, with R1 prime X, then I do multiplication of the polynomials, but so I will get R0X, R1 prime X, but multiplication, I need to do it in K, and in K, I need to take modulo phi. So it will be this, and then plus R1X times R1 prime X modulo phi times X squared. Okay, so this is how you go about adding and multiplying polynomials in K capital X. Now, in K capital X, since it contains F, and phi originally was a polynomial with coefficients in F, I can consider phi with capital X as a polynomial in K capital X. Okay, but in K capital X, I have the element which I call, I can call it Rx. We called it pi of x. This is simply the polynomial x considered in K capital X. Okay, so it's simply an element in K. And just like I do in any other field, if I have a polynomial over a field and an element in this field, then I can substitute the element. I can evaluate the polynomial at the element. So I can do, sometimes it's denoted, you take the polynomial and you evaluate it at the element. But what happens now? Okay, I take the polynomial. Basically, I replace capital X by small x. So I get phi with small x. Phi with small x it must be an element in K, right? But phi with small x is equal to 0 in K, because in K I do modulo phi. So all in all, I get that this element, which we later denoted as alpha, is a root of phi x. So I can write phi x as x minus alpha times some psi x over K. Okay, and this is the heart of the matter. Once I can find a root for a prime polynomial, I can repeat this argument. Namely, I take K1 to be fx modulo phi. Then I know that phi has a root in K1. So in fact, what we showed is that K1 will be simply F adjoining some abstract element alpha that is defined by the property that it is a root of phi. And this F alpha is the minimal field containing F and some kind of abstract element that functions as a root of phi. And now phi phi at least, I can split at least one linear factor out of phi, maybe more, but at least one. That means that I can look at psi x over K1. Maybe not psi x, because maybe I can split more linear factors. But after I split as many linear factors as I can, I am left with let's say psi1 of x. Okay, and I can consider k2 equals to k1 x modulo the remaining part of phi, so psi1. And again, psi1 will have a root in k2, and k2 will be the minimal. So k2 will be k1. I mean, the minimal field containing k1 adjoining some root alpha 1 of psi1. And I continue. There could be only finitely many. I mean, this process has to terminate because the degree of phi is finite, and I am left with a splitting field. Okay, I mean, namely, I am left with a field containing, I mean, in which I was able to split all the linear factors that I could from phi. So phi completely splits. Is this clear in this existence?
Yeah.
All right. So again, it will be great if you prepare questions on whatever we did for the next time. It could also be on previous material on abelian groups if you want. And we will start with that next time.